So for the last example of a greedy algorithm in this course, we will look at a problem from communication theory. We will look at the problem of Huffman codes. So when we communicate, we have to transmit information from one place to another place. So we might be working in some language like English, Hindi or whatever, but if we are using computers, for example, to transmit our data, we know that they must send this information in binary strings. So our typical goal is to take an alphabet and then encode it over strings of 0 and 1 so that at the other end we can decode it and recover the message. Right? So if we have, say, the 26 lowercase letters A to Z, then it's easy to see that we need to, if we want to encode each letter as a fixed sequence of zeros and ones of a fixed length, then we will need to use 5 bits per letter, because if we use only 4 bits, we can only get 16 different combinations. So with 5 bits, we can get 32 different combinations. So now a natural question is, can we do something clever about using different length encodings for different letters so that more frequent letters get sent with shorter encodings? Right? So can we optimize the amount of data we actually transfer in order to send a message from one place to another? So this brings us to the idea of having a variable length encoding, where we use different strings of different lengths for different letters in the alphabet. So one of the most famous examples of a variable length encoding is the classical Morse code, which was developed by Samuel Morse when the telegraph was invented. Right? So this was done using a mechanical device by clicking on a contact, and it would produce long and short clicks. So the short clicks were called dots and the long clicks were called dashes. We can as well think of them as representing the bits 0 and 1. So in the Morse code encoding, different letters do have different encodings. Now in English, E is the most frequent letter and T is another very frequent letter. So Morse assigned them codes of a dot, that is 0 for E, and a dash, that is 1 for T. Then Morse picked other frequent letters such as A and gave them 2-letter encoding. So A is encoded as dot dash or 0, 1. Now the problem with Morse's encoding is that it is ambiguous when you come to decoding. So for instance, if we look at the word, the sequence 0, 1, okay, then we don't know whether we should interpret each of these as a 1-letter code and get ET, ET. Or for instance, we should think of this as two 2-letter codes and get AA and so on. Right? So depending on whether we stop at a 0 or extend 0 to 0, 1, we can get many different interpretations. Now, in practice in Morse code, what used to happen is that the operator gives a slight pause indicating the end of the letter. So therefore, effectively, Morse code is not a binary code, but it's a 3-letter code, 0, 1 and pause. Now, when we are using, of course, digital computers, we don't want to go to 3 letters. So we want to efficiently do this using just 2 letters. So in order to make a variable length code and unambiguously decodable, we need what's called the prefix property. Okay? When we read through a sequence of zeros and ones, we should be unambiguously clear whether we have read a letter or there is more to read. We shouldn't be like the earlier case where we have read 0 and we don't know whether we stop at 0 and call it an E in the Morse code setting, or we want to call it an A, which is a 0, 1. Okay? So we are going to use this capital letter E to denote the encoding function. So E of X is the encoding of the letter X. So here is an example. So we have 5 letters A, B, C, D, E. And now you can check that none of these encodings can be extended to anything. I don't have, if I see 1, 1, it must be an A. There's no other code which starts with 1, 1. If I see 0, 0, it's not a code, but 0, 0, 1 is a code. So 0, 1 cannot be extended and so on. Right? So each of these cannot be extended to be the code of any other letter. So now when we get a long sequence like this, there is no doubt. Right? The first point where I have completed a letter is 0, 0, 1, and this is a C. The next point where I have completed a letter is 3 zeros and it's an E. Then I read another C, and then an A, and then a B. Right? So if we have this prefix code property, that is, no letter is encoded to a string which is the prefix of the encoding of some other letter, then we have unambiguous decoding possible, and this is very important. So our goal is to find optimal prefix codes. So we need to talk about what we mean by optimality. So remember we said that our goal is to assign shorter codes to more frequent letters. So somehow we have to determine what are more frequent and less frequent letters. Right? So people have measured the frequency of the occurrence of each letter in different languages. So this is a very language specific thing. Right? So this optimality, something which is optimal for English may not work for French or for any other, Spanish or something. So you take a large body of text in a particular language, right? And then you count the number of A's, B's, C's, D's, and E's, and then you just look up the fraction out of the total number of letters across all this text. How many are E's? How many are B's? How many are C's? So this is a kind of statistical estimate, right, of the average frequency of this. So this frequency will be a fraction. What fraction of the letters over a large body of text will be E's? What fraction will be C's? And these fractions will add up to 1, right? Because every letter must be one of them, right? So the fraction of A's plus the fraction of B's plus the fraction of C's and so on is going to add up to 1. And because of this, we can also think of this statistical estimate as a kind of probability. Like if I give you a random letter, if I look at a piece of text and I pick up a random letter from that text, what is the probability that it's X? Well, it will just be the frequency of X across all the text, right? F of X. So these will add up to 1. So now we have a message which consists of some n symbols, right? So we have M1, M2 to Mn, right? So these are my n symbols. Now we know that if I pick a particular letter X, then Fx fraction of these are X, right? So in other words, if I take n and I multiply it by the fraction, so say if Fx is say 1/3, then 1/3 of n, so n by 3 of these symbols will actually be the letter X, right? And now each of these X's is going to be represented by its encoding, right? So supposing it is 0, 1, 0, then each X is going to be represented by 3 bits. So then n into Fx is the number of times I see X, and this into the length of this encoding is going to give me the total number of bits taken to encode all the X's in this message. Now if I do this for every letter, okay, so if I take the summation over every Y or every X in my alphabet of n times the frequency of the letter times the encoding length of that letter. Okay? So this tells me how many bits I need to encode that particular letter. I add up all the letters, I'll get the total length of the encoded message, right? And if I don't include this n, okay, because notice that n is not part of the summation, it's an independent thing, it's a fraction of any n. Okay, if I just look at the total weighted average of the lengths of the encodings, then this is, if you studied probability theory, what is called the expected length of the encoding. So this is the average number of bits I use for a letter. Okay. So let's work out how this. So suppose we take our earlier example of 5 letters. Now we insert some fictitious information about frequencies. So all these 5 values are fractions between 0 and 1, and they all add up to 1. Then if I do this summation over X of f of X times the length of E of X, okay, then I have 0.32 times 2 because the encoding of A is 2 letters. Okay, then I have 0.25 times 2 because the encoding of B is 2 letters, and so on. Right? So I have these 5 terms A, B, C, D, E, and then I add it up and I get 2.25. Right? So it says that I need on an average 2.25 bits per letter. Of course, I can't use 0.25 bits per letter, but what this says is, for instance, that if I have 100 letters, I would expect to see 225 bits in the output encoding. Now, a very specific kind of prefix code is the fixed length code, where just by the fact that every code is of a fixed length, I know exactly where each one. So supposing I use 3 bits in this case, if I want a fixed length code of this, then there are 5 letters, so I can't do it with 2 bits because I'll only get 4 different combinations. So I need 3 bits. So if I use some 3-bit code, okay, then every 3 bits will be 1 letter. Okay. So in the fixed length encoding of this, I would use 3 bits per letter. So therefore, clearly the number of bits per letter is 3 because I'm using 3 for every one of them. And so by going to a variable length code encoding which takes into account the frequencies, I'm actually saving, instead of sending 300 bits for 100 characters, I'm sending it 225 bits. So you have a 25% saving. Right? So this is what we are trying to get at. So in this example, in the previous thing, we had 2 frequencies, right? 0.2 and 0.18. So 0.18 means D is less frequent than C, but somehow we had assigned C to be a longer code. So this violated our basic principle that shorter code should be assigned to more frequent letters. So if I see a pair of letters which are where one is more frequent than the other, I expected to get a shorter code and I had not done so. So if I invert that, right? So supposing I now assign a 3-letter code to D and a 2-letter code to C, then these two terms change. The other terms, though the encoding may have differed, the lengths don't change, right? So then I get, instead of 2.25, I get down to 2.23. Right? So what this says is by looking at different encodings, I could get different ABL values, right? This average bits per letter. So now our goal is to find an assignment capital E which minimizes this quantity so that our coding is as efficient as possible. So to get to this, it's useful to think of these encodings as binary trees. Right? So in a binary tree, I can interpret the directions as 0 and 1. So typically left is 0 and right is 1. So now if I read off a path in a binary tree, it is also a binary sequence. So this path is 1, 1 on the right, for example. Okay? And this path, for example, is 0, 1. And this path is 0, 0, 0. Now if I read off a path, and then I find a letter at that label, then it's as good as saying is that that path labels that letter, or that letter is encoded by that path. So here, because E has the encoding 0, 0, 0, in the binary tree, I will follow the path 0, 0, 0 and label that corresponding letter, that vertex, by E. Now because it is a prefix code, if 0, 0, 0 labels E, there will not be any code which says 0, 0, 0 and something more. There will not be another label below it. Right? So these labels will not extend to other labels. I will not find an F below D because otherwise it is not a prefix code. I do 1, 0 and I get a D, but I do 1, 0 something else and I get an F. So the code for F extends the code for D. This is not allowed. Right? So in a prefix code, this cannot happen. So therefore, all the labels are actually at leaf nodes. Right? They are at nodes which have no successors. So here is an encoding for the other scheme that we had, where we exchanged the values of C and D. So now C has a 2-letter code and D has a 3-letter code. So this is indicated by the depth now. The depth is the path, right? The length of the path is the depth of the node. So C in our earlier thing was at depth 3, right? And now it is at depth 2. And likewise, D was at depth 2 and now it is at depth 3, right? So we want to basically put things which have higher frequencies higher up in the tree at lesser depth. So having encoded our or looked at our encoding as a binary tree, we will now make a couple of observations, 3 observations about them, which will be useful to prove, to develop an optimal algorithm and prove it is optimal. So the first thing is that in such a tree, right, if it is optimal, every node will either have no children, will be a leaf, or it will have 2 children. This is what you call a full tree, right? So every optimal tree is full. Now it's easy to see this because supposing we claim we have an optimal tree in which somewhere in between we had a node which had only one child. Then this child can effectively be promoted. We can remove this node completely and we can shrink the tree along this direction and nothing will change. Except that the depth of the nodes below it will become less. So in fact, we will possibly get a shorter average bit length than we had before. Right? So therefore, by having a singleton, either only a left child or a right child, we cannot be optimal. So every node must have either 0 or 2 children. The next property is exactly what we saw in the earlier thing, which is that if I have 2 nodes x and y, such that x is higher than y, okay, so x is at some level and y is at a different level, then x has a shorter encoding than y. This must mean that f of x is at least as much as f of y. In other words, when I go down the tree, my frequency cannot increase. Because if f of y were bigger than f of x, that if I had more y's than x's in my text, then I would just exchange these two, right? I would find a better encoding by putting y here and x here. Because now if I do f of y times the length of y or the depth of y in this tree, okay, then it will reduce because the depth of y is reduced. and this is a higher multiplier. So therefore, if I had a higher thing below, then I could exchange letters and get a better tree. And that doesn't happen in an optimal tree. So then in an optimal tree, if I go down the tree, I'll only find lower frequency letters. The final property is to do with leaves at the lowest level. So supposing I have a leaf at the lowest level, right? So this is some leaf at the lowest level. So I know because it is an optimal tree that it cannot be an isolated child, it must have a sibling, right? So I go up and come down, it must have a sibling. Now there are two possibilities, right? The two possibilities are this is a leaf, okay? Or the other possibility is that this is not a leaf, right? The claim is that if it is not a leaf, then it must have children. So then there are leaves here which are at a lower level than X, but X is assumed to be a maximum depth leaf. Okay? So a maximum depth leaf cannot have a sibling which is not a leaf because its sibling would then have children which have a higher depth. Okay? So therefore, if I have a maximum depth leaf in my optimal tree, then it will occur as a pair with another maximum depth leaf. Right? So this is a conclusion that leaves at maximum depth occur in pairs. And then we know that because the frequencies keep dropping as we go down, increasing in depth, these pairs must have the lowest frequencies, among the lowest frequencies. So now in order to develop a solution, we will use recursion. So what we will do is we'll say, let us look in the overall table that we start with and pick two letters which have the lowest frequency. So we can assign them the longest codes. So they can be put at the lowest level. And then we know that the lowest level leaves occur in pairs. So let's assume that these will be paired up. Okay? So we will assign these lowest frequency letters X and Y to a pair of leaves at the maximum depth. Left and right does not matter because it's only the depth that matters. So now the recursive solution will say that, okay, how do I figure out what the rest of the tree looks like? Well, if I have a situation where I have decided that X and Y go here, okay, then I will kind of treat this as a unit and make a new letter called XY and give it the cumulative frequency Fx plus Fy of the old two letters. Right? So I'll construct a new alphabet in which I drop X and Y and I add a new composite or hybrid letter XY whose frequency is going to be Fx plus Fy. Now recursion kicks in. I have a k minus 1 letter alphabet. Okay, so I will recursively find an optimal encoding of that. Now, before coming to how to adapt the solution, the recursion ends when we have only two letters. For two letters, the optimal solution is to build a tree which has exactly two leaves labeled 0 and 1 as a path. Right? So this is the base case. So if I have more than two letters, I will recursively construct a tree for the smaller thing, and then I will come back, and now in the tree that I constructed, I will have somewhere a leaf labeled XY. Now XY is not a letter, so what I will do is I will replace this by two new leaves called X and Y. So I will go from the tree over A prime to a tree over A by doing this. Okay, so this is an algorithm developed by Huffman, and this type of coding is called Huffman coding. So let's look at this example that we had earlier. Right? So here the two lowest frequency letters are D and E. Right? So we merge them into a new letter DE, and this is a frequency 0.23 because it's 0.18 plus 0.05. Now these two are our two lowest letters, so we merge them and we get a new letter CDE of cumulative frequency 0.43, which is the sum of all the frequencies of the components. Now it turns out that these two are the smaller two, so I merge them into a letter AB. And now I have reached my base case where I have exactly two letters. So I can set up a trivial tree for these two letters labeled 0 and 1. Okay. And now I work backwards. So the last thing I did was to merge A and B. So now I will take this AB thing and split it up as A and B. Right? So I will split AB as A and B and I will get this tree. Then the previous step was to combine CDE into C and D. So I'm going to split this up as C and D. Okay. And finally I'm going to split this up as D and E. Right? So this is how Huffman's algorithm works. Right? By recursively combining the two lowest frequency nodes and then taking the composite node and splitting them back afterwards. So to show that this algorithm is optimal, we'll go by induction on the size of the alphabet. Now clearly when I have only two letters, I can't do any better than assign one of them 0 and one of them 1. So the base case is optimal. So we will assume that this is optimal for k minus 1 letters and now show that it's also optimal for k letters. So recall that we went from k to k minus 1 by combining the two lowest frequency letters as one, constructing an optimal tree for this smaller alphabet, okay, and then expanding the xy to get a new tree. So the claim is that when I go from the tree over k minus 1 letters to the tree over k letters, the cost is going to increase, but this cost is going to be fixed by whichever letters I chose to contract. So if I chose x and y to merge to go from t to t prime, then the amount by which the average bits per letter is going to change is exactly the frequency of this combined letter fxy. Right? So it's deterministically fixed by which one I chose. Even though I don't know the cost of the trees directly, I can tell you that the cost is going to be different by this amount. This is not very difficult to prove. Okay, so in that summation that we had, so in the tree notation, remember this depth of z is the same as the length of the encoding of z, because the depth exactly reflects the length of the string used to encode it. So this is our ABL calculation. Now for every node other than x, y and xy, they are exactly at the same position in t and t prime. So the summation, the terms don't change. So the only changes are between these three nodes. So what I will do when going from t prime to t is I will remove this contribution of the composite letter xy, okay, and then at the next level, which is 1 plus the depth of the xy, I will add the node fx and I'll add node fy, so I'll get the combination of fx times that plus fy times that. Right? So I'm subtracting this amount on the left, and then I'm adding this amount on the right. So now, actually, f of xy is nothing but fx plus fy. So this left-hand side term is actually this right-hand side component, depth of xy times fx plus fy. So I'm subtracting this and adding it back, so they cancel each other out. Okay? So therefore, all I'm left with is 1 times fx plus fy, which is fx plus fy or fxy. Right? So therefore, in going from t prime to t, the crucial thing is it only depends on which letters I have contracted. That fixes the difference uniquely. Now, let's assume that we know how to solve all k minus 1 size alphabets efficiently, and we have done this recursive thing to construct a tree t for size k. Suppose there's another strategy which produces a better tree for size k. Okay? So there's another tree, candidate tree S, produced by some different strategy, whose average bits per letter is strictly better than the one that we construct recursively. Now in S, we know for sure that these two letters that we use in the recursive construction, x and y, okay, so they occur somewhere at the bottom of this tree. Okay, so this is my tree S. Okay, so these must be leaf nodes because they have the lowest probability, lowest frequencies over all the letters, so they must be at maximum depth. But they may not be next to each other. But it doesn't matter because since they are both at maximum depth, I can move them around. At this depth, I can move letters around. I can reassign them to other leaves at the same depth, such that I come with a configuration. I come to a new S. I call it S again, where I actually have X and Y together. Okay, so I can assume that the S that has this optimal property, which is better than the T I constructed, actually has X and Y as sibling leaves at the maximum depth. Now what I'm going to do is in this S, I'm going to concretely fuse this and get an S prime. So this S prime will be over k minus 1 letters, except instead of doing it by a recursive call, I'm actually taking a concrete tree over k letters and I'm actually compressing two nodes into one and calling it a tree over k minus 1 letters. But because this is over k minus 1 letters and this represents an encoding, okay, it cannot be any better than the encoding that I recursively computed for k minus 1 letters because I assumed by induction that my algorithm works efficiently for k minus 1 letters. So S prime is no better than T prime. But S prime plus f of xy is S. T prime plus f of xy is T, right? So the difference between T prime and T and S prime and S is exactly the same. So if S prime is no better than T prime, then S cannot be any better than T, right? So it was a contradiction to assume that S was strictly better than T. So this proves that our strategy of recursively computing T is optimal for all K. A word about the implementation. Okay, so what we have to do is k minus 1 times we have to merge these two minimum values and compute a recursive solution. Right? So the bottleneck is finding these minimum values. If we use an array, then as we know, we'll have to scan the array each time to find the minimum values. Remember that the minimum values keep changing. I can't sort it once and for all because each time I combine two letters, I introduce a new letter into my array with a new minimum value which was not there before, or not a new value which is not there before, which may or may not be the minimum. So at each stage I have to find the minimum. So it's an order k scan each time, right? It's a linear scan, and I do this about k times, so I get order k square. But it should be fairly clear to see that this bottleneck can be got around by using a heap, because that's precisely what heaps are good at, finding the minimum, right? So if I maintain the frequencies not as a simple list or array but as a heap, then in order log k time I can find the minimum values, and then I can insert back the new composite letter also into the heap in log k time. So each iteration takes only log k, and so I improve from k squared to k log k. So recall that we mentioned at the beginning that this is going to be our last greedy algorithm. So why is this greedy? Well, because every time we make a recursive call, we are deciding to combine two nodes into one. And the two letters we choose are always the ones with the lowest frequencies. Now, what is to say that we could not do better by choosing the lowest and the third lowest, for example? But we never try it. Okay? We only try the lowest and the second lowest. So we make a locally optimal choice, and we keep going with this choice, never going back to revisit it, and finally we get a global solution. Now we have proved that this global solution is actually optimal, and we have to do that because there is no other reason to expect that by making this short-sighted choice at the current time, take the two worst frequencies and combine them, that you are always going to get the best solution. So this is very much a greedy strategy. So finally, a brief historical note. So Claude Shannon is the father of information theory, and when they were looking at these problems around 1950 or so, so they were faced with this problem of finding an efficient encoding. So Shannon and Fano proposed a divide and conquer thing. So what they said was, okay, let us look at the encoding of the alphabet. So some of them are going to start with 0 and some of them are going to start with 1. Right? So everything which is in the left subtree of this coding tree that we construct is going to have a code of the form 0 something something. Everything on the right is going to have something of the form 1 something something. So it seemed intuitive to them that a divide and conquer strategy is good. What if I put letters on this side such that they occupy roughly half the frequency weight of the total alphabet? That is, if I take the frequencies of all the letters whose encoding starts with 0, their frequencies add up to roughly half, and the other one also to half. So I split the alphabet into two of equal weight, assign some of them to start with zeros, the other to start with 1, and then I recursively solve this. Right? So I partition A as A1, A2. The sums of the frequencies in each of the sets are roughly equal. Solve them recursively. Unfortunately, this is not guaranteed to generate an optimal encoding. Right? So you can come up with examples where you can do this, and then you will end up with something which you can improve by doing some other thing. So it turned out that Huffman was a graduate student in a course of Fano. He heard about this problem and he thought about it, and after a few years he came up with this clever algorithm which we have done today.